Yes. Thank you, Paul. So I'm happy to say a few words on behalf of the selection committee, who made a decision to give the John Stuart Bell Prize to John Martinis this year. And the members of the selection committee, besides myself, were Jens Eisert, Se-Woo Nam, Michelle Simmons, and Vice Chair Paul Brummer. John Martinis and the study of quantum behavior in superconducting electric circuits goes back a long way to his PhD at UC Berkeley. And maybe John himself and also Michel Devereux will say a few more things about this in their talks today. And what started off probably as a very fundamental investigation has now led to developments which can also almost be called commercially successful with investments for many tech companies. And of course, I would say this is the beauty of science, the fact that yesterday's curiosity, in this case, John's curiosity and his drive, may lead to tomorrow's solutions. And in the development of superconducting qubits, John has played a very crucial leading role. He devised what was called the phase qubit. But interestingly, he also gave up this phase qubit, as far as I know, for a transmon qubit or an Xmon qubit, as Google developed it, since this could potentially function better in a multi-qubit device. He really relentlessly pushed for the best possible two-qubit gate, identifying this as a very essential component in his schemes. Another important contribution, he strived to understand loss and decoherence via very simple and intuitively, pleasing or interesting physical models and mechanisms. So the effect of two-level systems, quasi-particles, all that can go wrong with superconducting circuits, he studied and was interested in, or is interested in. In 2014, he moved to industry, to Google, to tackle problems head-on, gathering a very large team. And I presume that the reasons for this was that he found this a better environment to pursue his goals than academia. And I'd like to relate a small anecdote, sort of a personal thing, that more than 6 years ago, before John's move to Google, I remember asking my husband, David DiVincenzo, and this was before I was very knowledgeable about superconducting qubits. So I asked David, said, who do you think would be most successful in building a superconducting qubit quantum computer? Who really wants to get it done? He said, John Martinis, no doubt. Simple answer, and I think with visible consequences. So indeed, the Google team under his leadership had many successes. There were many beautiful papers. I have to say, I really also enjoyed what could be called the repetition code paper. And this was the first time anyone showed that with quantum information, more redundancy, more qubits gives better performance. So they showed that the 5-qubit code protecting 1 bit of information performs better than a 3-qubit code. And one could say this was just a protection of classical information, not quantum information, but it was a dry run for the surface code, which is still a point in the future. And so then the crowning achievement, I could say, that was enabled by these engineering successes that John was driving, you could say was this Google Sycamore chip with 53 qubits in 2019. And this experiment enabled the first quantum supremacy experiment. Well, what I could say, it was the first time that anyone dared to make a claim of quantum supremacy, a claim that said, we can do this experiment, this programmable experiment on a quantum chip that will be very hard to simulate classically. And here is how hard we expect it to be. Now, we all know that quantum supremacy may not be built in one day or one experiment. Classical algorithms can play some catch up for a while. So we're maybe a bit in a transition phase. But still, we expect that the effort, to add a few extra qubits stands in no comparison, let's say you add 10 qubits, stands in no comparison to the classical computational effort you need to do to include those qubits in classical simulations. So we really are in a new era, I would say. At the same time, adding more coherence to these chips is still challenging. And I would say also by no means is this field, nor John, done with its development. It's still, many challenges. and interesting developments ahead. So let me now summarize and state the concise prize citation in full form. The 7th biennial John Stuart Bell Prize for research on fundamental issues in quantum mechanics and their applications is awarded to John Martinis for his innovations in the design and control of superconducting devices. In particular, his leadership in devising low-error multi-qubit superconducting chips, which has resulted in the first plausible claim of quantum supremacy, ushering in a new era of computing. Congratulations, John. In real life, I would be shaking your hand, so I do this in this form now. And I look forward towards your talk. Look forward to hearing your talk.
Thank you very much. I really appreciate the award. And I would say I very much appreciate the committee recognizing the long series of experiments, collaborating with many people, because that's what was really necessary to figure out the technology and get all this working. So thank you for putting that in.
So let me then introduce the John Stuart Bell Prize recipient, Professor John Martinis, to give a talk about 35 years of superconducting qubits. John.
Okay, great, thank you. I'm glad we're done a little bit early to get to the talk, or maybe I'll have a few extra minutes, sure. But I'll try to be on time. So I'm gonna go to my slides now and start the talk. And again, I really appreciate the prize greatly. And it's fantastic to be able to talk about what we've been doing in the last 35 years to build this. And it's really interesting. I thought it was interesting to think about where we were at UC Berkeley with a very rudimentary experiment with a single qubit, and then decades later building a very complex chip whose results would have to be checked by a supercomputer. And there's lots of technology going and science going from the left to the right. And that's kind of what I want to talk about today. And thank you for the opportunity to talk about the history. I first of all want to say just thank you to the many collaborators who have made all of this possible. Of course, John Clark and Michelle Deveray at UC Berkeley, which was instrumental for starting this field and training me as a scientist. I'll say more about that later. I was at Saclay and then NIST and then UCSB. And then finally, I want to just list all the people on the Google Quantum Supremacy, some of whom were at UCSB. And it's really all the contribution by many, many people that happened. And in fact, the list that I really want to thank is much larger than this, because there have been many people in the field, not necessarily on papers together, but working together as a field, solving the problems in different way. And of course, talking to people and reading their papers. All this information has enabled us to build these kind of complex systems. And really thanks to everyone who has been working hard and doing really good science to make this happen. I now want to just start over the history, and let's just start at my UC Berkeley thesis in 1985 with John Clark, where we were looking at macroscopic quantum tunneling. And the idea put forward by Leggett is that although quantum mechanics was known to work for microscopic particles, electrons, nuclear spins, et cetera, there was no evidence that it would behave at a macroscopic level, say the center of mass of a ball, or for electrical currents, which are carried by many, many electrons. And motivated by this, there were actually a few experiments in before this, but in starting this, and really, I like to appreciate John Clark's advice here, is we thought, well, how are we going to really do this differently and do it well? It's a very fundamental question. You want to do it well. And basically, the idea here was to do an experiment where we compare experiment and theory with no adjustable parameters, which meant measuring the parameters of the system and in fact doing microwave experiments. And in fact, the key here was understanding this was not just taking the IVs and current voltage characteristics of devices, but this was actually a new kind of microwave experiment. And we had to think about the microwave engineering of that. And you can, in fact, see that on the left-hand side. We have SMA connectors, and we have coaxial lines and filters and the like in order to preserve a proper microwave environment for it. And in fact, to understand that filtering was critical. At first, the experiment really didn't work at all. And then even at 1 Kelvin, and then by doing the filtering, we got it to work. So in the end, we could take data that showed that some escape rate, it described as an escape temperature, went as the physical temperature at high temperature as expected. And then at low temperature, it saturated out to a value that was very good agreement with what we expect from theory. And this was a comparison with no adjustable parameters. And actually, we went to a smaller critical current junction with a lower frequency, and then that indeed saturated out at a lower temperature as expected. However, the real important result came from calibration, where we were, in the end, able to look at the energies levels of the system. And of course, for qubits and the future of the field, this was kind of the most important thing that we discovered. So in this experiment, we put a constant microwave excitation, and then we swept the current, which swept the frequency of the device, and we were able to see very clear resonances, which were corresponding to the 0, 1, 1, 2, and 2, 3. Classically, this was kind of a smeared transition, a wide transition, no structure, and you were able to very clearly identify the energy levels. And of course, that's a great qualitative and quantitative too description that the physics was quantum and working properly. So after working with John, I then in a postdoc went to Saclay with Michel Devereux and Danielle Esteve and Christian Urbina. They had just started a project on this subject. And we came up with a next experiment where basically we were trying to measure the time it took to tunnel, time under the barrier, traversal time that it took under the barrier while tunneling. And this was actually come about from understanding the physics a little bit more. So the device here really was totally trying to understand what microwave transmission lines did. This was kind of the first experiment doing that. And you can see here in this schematic, they were more sophisticated engineering of the device. We had a much smaller chip now with proper coplanar lines coming out of it, going to a delay line of a high impedance and then terminated by a load, dissipative low impedance. And the basic idea was when the load was close to that, the low impedance would suppress the tunneling since dissipation suppresses tunneling. And then when we pull, actually with the string and a dilution refrigerator, pull the load back, you would then see a higher impedance of the delay line, and then it would be less dissipation. So when you took the data of this escape time versus this transmission line delay, what you saw at high temperature, there was a very small change in the escape rate as you expect. It's a prefactor effect. But when you went to low temperatures and it was tunneling, you then saw a very large effect, having to do with this physics I described. From the characteristic time of the change, which was, let's say, 50 picoseconds or so, that characteristic time is the characteristic traversal time that we are trying to measure. Okay, so we go on, and then at NIST, I started on a serious effort to look at qubits, and in fact, to build a quantum computer. In the intervening 10 years, there have been a lot of beautiful theory to develop this. But, you know, frankly, what happened at the time is that there was funding from the government to actually try to build a quantum computer. And this motivated to really start looking at this. Here's the first phase qubit data that we took with the Rabi oscillations. And you can see it had something like 10% visibility. It showed that that everything was working okay, but it was, let's say, not a very good qubit. But at least we were, you know, seeing a signal and could know that the system was operating properly. In a few years later, we were making 2 qubits. You can see that this is a complex design of the phase qubit to isolate the biases from the qubit. In this particular case, we had a capacitor coupling between 2 qubits, and we were able to do a 2 qubit with a simultaneous measurement of the 2 qubits. And it was kind of the precursor to all the experiments we were doing. So we started in the 0-0 state. We put a pi pulse in one of the qubits to the 1-0 state. We then watched it swap for some amount of time, and then we measured it. And then by doing that, you could see the oscillation between the 1-0 and 0-1 state, as you saw here. So the device was working properly. You could, in fact, tell what the phase of the oscillation was and see the like. So things are working. We were able to make gates, but you know, clearly if you look at this, the coherence time and the visibility needed to be improved. And because of that, one of the big things we did at the time was looking at qubit coherence. And this was, you know, really started at UCSB. And one of the things we initially worked on was dielectric loss. And here it shows that amorphous silicon, a common amorphous material, had a tremendous amount of loss. So let's say 10 to minus 3 loss tangent, clearly a bad material. You could use some materials to make it better, but okay, this was a problem. Also, this kind of problem with dielectric loss was seen in the junctions too. Because of their small size, if you take like a transmon, you generally don't see much of this effect, but the large size of the phase qubits, you really saw it be significant, so we would have to do that. You know, over the years, we also looked at quasi-particles, and this is an example where we had some shielding in our system, but if we did kind of an overkill, a shielding, we were able to get Qs much higher. In fact, it was understanding infrared radiation, creating quasi-particles. Once we finally figured that out, we were able to make lots more progress on the devices to get it to work. So in 2008, what I want to do is talk about what was, I think, the experiment we did in this whole series that really made me think that we had something that might work very well. And that's because we could do an experiment in some sense better than what other people with other qubits that have been around for a long time. We could start doing it maybe a little bit better than that and make complex states that had never been done before. So the nice thing here is we had fixed our qubits. We now had about a 1 microsecond coherence time. So that's maybe about 50 gate operations before you lose coherence. And this is a swap spectroscopy where we put, as we saw before, we put an excitation in the qubit and we swapped it to the resonator. And you can see a very nice swapping, but the important thing is the color scale here, where we're swapping between 0 and near 1. So it's high amplitude swap operations. The device is really working properly. So here we had a phase qubit. We could drive it in the normal way. And the phase qubit was also coupled to a resonator. And what we were able to do is change the qubit frequency to bring it in and out of resonance, as shown here, at the very short nanosecond timescales. And that way we could turn on the interaction by bringing it close to resonance and off by bringing it away. So for example, you can do an experiment where you put a photon in the qubit, a 0 to 1 transition, then connect it to the resonator for a certain amount of time so that it would get swapped into the resonator and then bring it out. And then you can bring another photon creating Fock states. eventually, after several experiments, we were able to make very complex states, which you can see here, which were, in this particular case, the 0+5 state in the resonator. And here's the Wigner function of the two conjugate variables. You have a pseudo probability, and here's the theory, and here's the experiment, with the red thing here being negative probabilities, showing indeed that you have a proper quantum state. Here's the density matrix. And here's a more complicated 0 + I3 + 6, very complicated state. Again, we were able to do the Wigner tomography to show that you indeed are creating this state. So what happened here is we developed digital waveform synthesis, we did precise digital control and calibration, and we showed that with the superconducting qubits, it was indeed possible to calibrate and then run, once you do the calibration, just run the experiment to get very precise quantum states. And well, once we saw that, it was stable overnight, for example, we really thought there was a lot of things to do, and this was an extremely good candidate for building a quantum computer. Of course, we did an experiment that violates Bell's inequality. Here was 2 qubits in a resonator, another qubit. Here's the picture. We put a 1 state in qubit A, then did a half swap to put an entanglement between A and the resonator, and then did a full swap between the resonator and qubit B to create the entangled state. And then with a rotation, which is basically a change of a measurement of the axes, we measured it. Here's the Bell's inequality with a Bell's inequality greater than 2 violated it. Now, what was interesting and different here is we showed Bell's inequality in this superconducting system, but we did it where we closed the measurement loophole, where every time we did the experiment, we recorded the event and then calculated Bell's inequality. There was no kind of post-selection or the like. And I thought that was, kind of an interesting contribution. But I would say the real thing that we understood technologically here is worked hard to build a high fidelity system everywhere for the qubit operations, reset, for the measurement, and, pushing the fidelity up, it really enabled us to do this. Another thing briefly talk about is a nice experiment with Andrew Cleland, where now we were using the phase qubit as a probe for another macroscopic quantum system. In this case, it was a mechanical resonator, which was piezoelectric, so that it would couple to the qubit given here. Here's the coupling capacitor, here's the mechanical resonator, and doing essentially the same experiments we did before with an electrical system. We were able to see avoided level crossings. We were able to pump a photon and see a single excitation in the mechanical resonator and understand that. And I would say this was really an amazing experiment for Andrew's group, in that this required something like 15 steps to both build the qubits and do all the mechanical resonators. So it was a real experimental tour de force. Now what I would say is talk a little bit about error correction and the surface code. And this was very important because it basically changed the direction of the group. And from this, we finally understood what we had to build an error correction quantum computer and what the future was in the field. And I really thank Andrew Cleland and Matteo and Austin Fowler to push this paper forward and understand. And it was kind of interesting at the time. It was a paper where we actually didn't, it was just a little bit new in there, but what we were trying to do is make the surface code very clear so everyone could understand what to do next. And particularly, I wanted to know, how to design the quantum computer. And the nice thing about the surface code is when you had, you just built it with a square array of qubits, where each qubit was only connected to the 4 nearest neighbors. And because of the limited connectivity and the nearest neighbor connectivity, this is why, kind of as Barbara mentioned, I abandoned the phase qubit. The phase qubit had a very large capacitance, and I thought about a computer, I thought about steam code, long distance communication. I always thought that large capacitance would be an advantage for systems engineering. But once I understood the surface code, it was very clear that the transmon could do this. And given that it was higher coherence, then that was the thing to do. So given this understanding, we then did a series of experiments, basically one big experiment per year to push forward to try to test the surface code. So the first thing we had to do is move from phase qubits to transmons. And I very much thank the Yale group for beautiful papers and beautiful experiments so that we were able to do that without a tremendous amount of work. But basically, we just took what we knew from the phase qubit and inserted the transmon and did the resonator readout. And all these, took some time to figure that out. At the time, most people were making 3D transmons because they had long coherence times and the like. We wanted to make an integrated circuit to make it scalable. But at the time, the coherence time of IC transmons were not so great. And I would say the big thing in this experiment is we showed that we could get coherence times that were reasonably enough to do good experiments. Here, the T1s was about 40 microseconds and the T2s maybe around 20 microseconds, a little bit more maybe in some, and that enabled it to do that. So we built a tunable transmon with the Z control. This is just like the phase qubit. We had the standard XY control. We were able to connect it to a bus and able to connect it to resonator and readout. And basically we could use a lot of the infrastructure that we had developed for the phase qubit. So this was in 2013. In 2014, we just took that and scaled up to a 5-qubit device and took some effort to figure out how to do that. We basically had a linear array of transmons with the X, Y, and Z control coming in on one side and a frequency multiplexed resonator readout on the other side. And you can see that in the picture here. And then we were moving the qubits up and down in frequency, bringing them in and out of resonance to do the control. So one of the things we did at the time was trying to very precisely characterize this with randomized benchmarking, and that was becoming very popular and important at the time, and this allowed us to benchmark this complex system. For single qubits, they were about 99.98%, which is compatible with the 20 nanosecond gates and the 20 microsecond coherence times. But the big thing we were able to show was that the control Z entangling gate was quite good, about 99.5%. And here's an example of interleave benchmarking showing that it's very good. And here's an example of the control pulses coming into this, just showing that at this point we were running very long sequences, many qubits running at the same time. And we were able to develop the device where we didn't have too much crosstalk, and we were able to do complex things. And for example, we were able to make G8Z states with this 5 device. So this was a really important development. And I would say the most amazing thing about this experiment is that it worked better and faster than I had thought. I mean, that's like the only time in my career that has happened, and gave us confidence we were on the right road here. We then built a 9-qubit device, and the difficulty here is we had to have interleave measurements so that during the algorithm where we're repeating it, we were doing measurements at the same time. So in terms of the big surface code, we were just doing a 1D cut of that and only doing bit flip. But you can kind of see here that there are similar to what we did. So the big thing here is if we use 9 qubits, and we repeated this many times, we would get a fidelity. Of course, that gets worse over time. But if we went to fewer qubits here, then it got even worse. And this improvement with scaling up the number of qubits is exactly what you want to see with error correction. And the amount of improvement was about 3.2, which means if you continue to make it larger and larger, the errors will get smaller and smaller. And indeed, there's a recent paper by Google with, I think, up to 22 qubits, where they indeed see it scaling better and better. Here's some data showing that the errors are going up versus time. There's leakage of the two-state that you had to deal with. And that's, of course, what has been going on in the last, 7 years or so to figure out and improve that. But basically with this, we saw that things are working well, and it gave us understanding what to build in the future and build a 2D code. And it was a very important experiment to kind of test the ideas here and know what to build next. In order to get this work, there's a lot of things, infrastructure we had to build. And again, we want to thank the Yale group and others for inventing and perfecting parametric amplifiers and writing beautiful papers on how that worked. Our particular contribution was to make a wide bandwidth amplifier, which we needed for these frequency multiplex qubits. And here's an example where we just used a simple parametric amplifier, but what we did is we do an impedance matching from 50 ohms to 15 ohms. In fact, this would improve the bandwidth. Also, we discovered, we didn't invent this, we just discovered from observation that putting a low Q resonance mismatch here, you could tune in the phase to get things to work right. So here's the device, complicated transmission line. We are used to do that. And then here's the results showing that a gain and noise were good and near the quantum limit for about 600 megahertz of bandwidth, instantaneous bandwidth. And this, of course, was what we needed to get the experiment to work. The other thing that we also worked on, for example, was fast. We had to do fast and accurate measurement, doing measurements in the order 100 nanoseconds. And we basically took the idea of putting in a Purcell filter, but we, in this case, tried out using a bandpass for Purcell filter. So you have a qubit, you have a resonator for readout, you have a Q of about 10 filter after that. And if you look at the amount of power going through the port here, the qubits are about at this frequency, 5.5. You can see the resonator sitting here. Normally you have some isolation because the qubits are off resonance from the resonator, but not too much. But because of this background resonance from this second Purcell filter, you can then decrease the coupling off resonance, and then there's less effect on the qubits. And that secondary resonance, for example, is given by this transmission line here, properly designed. And with this, if you looked at the performance of the readout versus pulse integration time, the performance gets better as you increase the integration time, but then leveled off at about a 1% error level when the integration time was such that you had T1 decay of the qubits. But things worked well, and clearly we could go fast, and others have gone even faster, but you could get the appropriate kind of 1% errors and fast if you design everything properly. So this is what helped us do the experiment. Other Qubit improvements, we learned about surface contaminants, had to do special processing. There was radiation loss because the various ground planes were interrupted by our coplanar lines, and we had to strap them together. Big issue with leakage to the second excited state, non-qubit state. And by carefully adjusting and controlling this out of quadrature phase, you could take a fairly large leakage population to the 2-state versus number of Cliffords, and then reduce that quite significantly. And in fact, in the latest Google experiment, they did techniques to reduce this even more. So this is a very important thing you have to worry about. Also worked on tunable couplers at the time, which has led to the Sycamore chip. Basically, we did, instead of capacitive coupling, we did inductive coupling with the coupling and inductance with setting the flux properly could go to infinity and turn it off. This is a plot of the coupler bias versus the splitting between the two qubits. And you can see there's a bias where there's no splitting and the coupler's off. And then we could turn that on quite significantly. And this could be done with high fidelity. So there were very nice experiments doing here. Here's an experiment of 3 qubits, adjustable couplers with a RF drive to it. This would allow you to make a coupling that had either the I phase associated with it. And this could be used to simulate, for example, what happens for a magnetic field. So in this experiment, without the proper phase in there, you see the excitation going from the blue qubit to the green and red qubit. And then if you adjust things properly, you see that it's circulating, in this case, from blue, green, red, according to the synthetic gauge field. And here's a simulation of what would be a 2D lattice. The dots are the experiments and the lines are the theory. And what this means is you're now being able to calibrate these devices very precisely in a global sense, in a system sense. Okay, so this leads to the quantum supremacy experiment. Going to Google, we wanted to do the error correction, but along the way, motivated by Scott Aronson and the boson sampling, we decided we could do a quantum supremacy experiment, which had twofold to it. One, we wanted to show Silicon Valley executives, Google executives, that a quantum computer actually could fulfill its promise and be powerful, at least in a crafted problem. And secondly, I wanted to know if when we ran a complicated algorithm, whether something horrible would happen to the errors and cause you not to build a quantum computer. So we did that experiment. And again, the quantum supremacy, 200 seconds on a quantum computer, it had to be checked with a superconductor, would take a very long time. A Sycamore processor, 53 qubits in a square array with the 4 nearest neighbor connections. This was forward compatible to do surface code error correction. So we wanted to build it that way. And note that we're using new adjustable couplers here to turn on and off the interactions between the qubits. So that was added. And here's the chip with all the many wires going on the outside, bump bonded, indium bump bonded to the qubit chip to do all the interconnects that you need to do in such a complex chip. This is, of course, put into a dilution refrigerator with our preamps and many wires going to room temperature. And then those wires go to, rack mounted control systems where we can synthesize the waveforms to do all the control. And of course, there's tremendous amount of software going on there. I do want to mention the important part of this is calibration, learning how to execute the quantum computer. There's a lot of things going on here to calibrate and check what's going on. To give you a scale of this, these 2 dots here was the PhD thesis of Jimmy, where he was thinking about the 2-state leakage and stuff. So this is incorporating many, many years of experience by the group in order to get this to work. Okay, so the control sequence was this, is basically what you would expect for a general purpose quantum algorithm. The circles are a single qubit operation. The lines between them is a 2-qubit square root I swap that. And the control sequence is exactly what you would need for a general purpose algorithm. For the particular quantum supremacy experiment, we have pi/2 rotations along the X, Y, and in between axis with the swap operations going around. And then we have a 12 nanosecond 1 qubit 2 qubit gate and about 25 nanosecond single qubit. So it's funny that the 2 qubit gate now is able to be faster than the 1 qubit gate. So the quantum supremacy is you do this random circuits, you sample what will be the highest probability states. You then take the same circuit, compute it on a, say, a supercomputer, a computer, get the probabilities, then measure this cross entropy fidelity. And basically, since you're measuring the high probability states, P should be greater than 1/2 to the n, and the fidelity would not be 0. So fidelity is 1 if it's perfect max, 0 if it's any error at all, 1 error, 2 errors. And this allows you to check the system, do system validation, learn the control map, quite useful. So here's the quantum supremacy data, the red circle in the red circles. And this goes from 12 to 53 qubits. And when we run the circuit and then do the check with the cross entropy fidelity at 12 qubits, that's about a fidelity of 40%. More or less what you expect for 250 gates and the fidelities we did. And of course, as you add the number of qubits, that fidelity goes down. It gets harder and harder to check from a laptop, the workstation, and at the very end, you're looking at, let's say, 5 hours of a data center, okay? We can also take the circuit and break it into 2, so it's exponentially easier. We call that patch circuits. More or less the same data because you're not cutting away too many gates. You can do somewhere in between where you only have a small number of gates here. But basically all that lies on top of each other. This was computable because this particular sequence allows you to use a mathematical trick. Quantum supremacy changes that, where you no longer can do the full circuit check, take too long. But the proxy of the patch and elided enables you to get what would be the answer if you did full. That's the 5 sigma, statistically different than 0, gives sensible results. Finally, I want to mention the black lines here. There's a prediction from gate and measurement errors, which also lies on top of the circuit. And that's kind of one of the most important things about the experiment. We have the same fidelity, full elided patch predicted. The errors do not depend on entanglement. In terms of prediction, it's just from the 1 and 2 qubit errors and measurement errors, you can predict kind of in a classical high school probability formula what the fidelity is, and that actually predicts it right well. This is what you expect, but it's good to see that it happens. And of course, this is good. So I'm gonna finish up here. Thank you. I'm running a little bit over time. What I want to do here is just really emphasize the reason all these NIST experiments worked was because of the field's focus on physics. It started at Berkeley, comparing the experiment with no adjustable parameter, many beautiful experiments, application, the theory, the clear theories were developed. People did complementary experiments where we could learn from each other. And I think, one of the reasons we've gone so far in this field is because the field has been, really working well together. And again, I thank everyone for their contributions to make this happen. And finally, I want to thank the Google team for the quantum supremacy experiment. It's only with the team working together, working hard, inventing a lot of things that all this was possible. Okay, thank you. I'm sorry, a little bit over.
That's okay. Thank you very much. This was a very beautiful, clear talk. Are there any questions? I didn't see any questions, which is always the sign of a clear talk. If anybody does want to ask, can you please raise your hand? And we will recognize you and do appreciate that you will be recorded. So I don't see any. Dvira, do you see any questions? Or Lillian?
Not yet. Not yet. There was a brief hand.
A brief hand. Well, that's an interesting.
Oh, I have a question, if no one.
Please go ahead.
Thank you very much for a beautiful talk. So I guess naturally the question is what's coming next? What do you think is the next challenge? Maybe small challenge, but also the big challenge in coming.
Well, obviously, Google and other groups are working hard to start scaling up the quantum computer. And, you know, this is really great that that's happening. You know, there's a lot of talk about scaling up the number of qubits, which of course is very important. But my statement has always been, we need to improve the qubits, because right now we're a little bit below the surface cold threshold. And in fact, if you look at the latest Google experiment, you know, the net system is a little bit above threshold. So we need to improve the qubit. So I wrote 2 papers this year, both one on the effect of cosmic rays, and there's experiments at Google. And also I've written one on kind of tapering the junction wiring and understanding the surface loss mathematically a little bit better. So I'm actually working with the group right now to try to improve the qubits and improve the coherence. The good news here is that the quantum supremacy experiment Google was done with the 16 microsecond T1 qubit. And the performance of qubits around the world generally much better than that. Of course, when you build a complex chip, things can get worse. But I think there's a lot of optimism for me, for example, that, you know, we should be able to make our qubits much better and then get closer to that. So in my view, right now, what I'm trying to work on is really understanding how to improve the coherence and make sure that's better. Of course, we have to work on scaling too.
Mm-hmm. Yeah, thank you.
Well, we have 3 in the Q&A. I'm not sure we can get them all in the time, but Mustafa Tuni asks, when do you expect we see the first quantum supremacy in commercial space, not just lab experiments, and what would that commercial application be?
Yeah, that's a really good question, because it's a lot harder to work on a useful algorithm. And, you know, people are still working on that. And, you know, the nice thing here is if someone were to cleverly come out, it could happen any year now, any day now, okay? But that's going to be hard to do. And it may take building an error-corrected quantum computing. So it's kind of from any time now to maybe 10 years or more till we do the error-corrected quantum computer. And it's a matter of merging the performance of the experiment with the performance of what you need for algorithms. So yeah, it's hard to predict that, but it's an exciting time because you know, we're working to close the gap, and it's not clear exactly where we are, and one idea could change everything.
Great. This seems like an in question from Peter Morgan. Says, hi, John, thanks for your talk. Do you think Google are on the right track with quantum computing? Initially, you said that you left Google because you didn't believe they were taking the right direction. What are your latest thoughts on this matter?
I'm going to say I disagreed in the direction, not necessarily technically, that was pretty clear what to do, but kind of the way it was managed, and it just didn't fit my style. And that's fine. And, you know, they're doing it that, and I'm going to do my things. And, you know, we just have to wait and see what happens with Google. I wish them all the luck. I hope that they make things right. And, you know, I'm trying to stay in the field and do some things that I want to do. And we'll just see what happens.
Great. Thank you. I'm going to leave it at that. The other questions you sort of answered in passing. In the interest of time, let's move on to the next talk by Professor John Preskill from Caltech on classical shadows of quantum states.
All right, thanks very much. I'm honored to be here. My announced title was Classical Shadows of Quantum States, and I do want to talk about that. But I'd like to start with some reflections appropriate to this occasion. First of all, like so many of us in the quantum science community, I greatly admire John Martinis and what he's accomplished. I heard John give a talk at Caltech in 2003 when he was still at NIST about efforts to improve the coherence of phase qubits. It was clear then he had big ambitions, and then he came back 10 years later with a more concrete plan for building a fault-tolerant quantum computer, which so far has been executed brilliantly, as the Bell Prize is recognizing. So I'd like to congratulate John and to thank him for the many inspiring contributions that have advanced our field, which were beautifully reviewed here today. It's a bit sobering to realize that it's been a little over 40 years now since Richard Feynman first proposed the idea of a quantum computer that for certain purposes can perform tasks that are beyond the reach of classical computers. And it's been 27 years since Peter Shor discovered the factoring algorithm that caused a big surge of enthusiasm for the subject and drew many people into the field, and including me. We made a lot of progress since then, but we still have a ways to go before we have really practical quantum computers that can solve problems we care about. Evidently, it's hard to build a quantum computer. It's hard because we want quantum computing hardware to simultaneously meet a set of criteria that are difficult to satisfy simultaneously. We want qubits to interact strongly with one another so we can rapidly process the quantum information they encode. We don't want the qubits to interact with the environment, which causes decoherence and the failure of the computation. But we do want to control the system from outside and in the end read it out to get the result of a computation. It's very hard to simultaneously satisfy all these desiderata. So it's taken heroic efforts by people like John and Michelle, improvements in qubit design and materials and fabrication and control methods to get as far as we have. I think it's important, as was just addressed by the last question in the previous session, to continue to pursue a number of paths to building quantum hardware. These different hardware approaches have their characteristic advantages and disadvantages. They may find complementary applications. There may be unexpected developments which can suddenly change the outlook. So I'm glad that these different approaches are all being pursued in parallel now. What Shor emphasized is there are problems that we should be able to solve with quantum computers that we can't otherwise solve, which have nothing directly to do with quantum physics. Of course, we'd like to understand better what those applications are that quantum computing can speed up. We've learned some things about that. Very likely, we still have a lot more to learn about that, but 40 years after Feynman, 27 years after Shor, as best we can currently foresee, the most likely way in which quantum computers will have a big impact on humanity is through the speed up of applications to quantum problems, like the study of chemistry and materials. Those applications can eventually improve human health and energy production and agriculture and the sustainability of our planet to the benefit of us all. And for a physicist like me or like Feynman, it's exciting to contemplate how quantum computing technology will allow us to explore nature in new ways and learn about the physics of very complex quantum systems. What Shor and before him Feynman were emphasizing is that quantum systems provide extravagant resources which we can exploit in quantum algorithms to do things we couldn't otherwise do. But just as important for its implications in the long term for technology and science is the principle of quantum error correction. That's our basis for thinking that we can scale up quantum computing and make very complex quantum systems behave in an intrinsically quantum mechanical manner. One of the things that makes quantum information profoundly different from classical is that we can't observe quantum systems, unknown quantum states, without disturbing them in uncontrollable ways. And that means that if we're going to run a quantum computation, we need to keep the information that's being processed from leaking to the environment. We need to keep it nearly perfectly isolated from the outside world, which is very difficult, but we've understood for 25 years in principle how to do that using the idea of quantum error correction. The essence of the idea being that if we want to protect a quantum state, we should encode it in a highly entangled form with the information shared among the parts of a large system. So when the environment interacts with the parts one at a time, that information is very well concealed and therefore is not damaged. And we've understood as well how to efficiently process information that's encoded in this very highly entangled form. And that is the path to large-scale quantum computing that we expect to pursue, which John and Michelle are already helping to lead the way. Really what Feynman 40 years ago and Yuri Manin around the same time were pointing out is there an essential difference between the quantum and classical world is that we don't think in general quantum systems can simulate, or classical systems can efficiently simulate quantum systems. Arguably, that's one of the most interesting things that has been claimed about the difference between quantum and classical. So there's a strong incentive to the extent that we can to validate that claim in laboratory experiments. And that was the challenge that the Google AI quantum group responded to when they built Sycamore. As we've heard, Sycamore is a fully programmable circuit-based quantum computer with 53 working qubits laid out in a two-dimensional array, such that by tuning coupler qubits, we can execute two-dimensional entangling gates on neighboring qubits in the array. The Google group executed circuits with up to 20 layers of those entangling 2-qubit gates with randomly chosen single qubit gates in between. Because the device is noisy, when they read out the final result at the end, they got a valid result only 1 in 500 times. But by repeating the same computation millions of times in a few minutes, they could get a statistically useful result. And if we wanted a classical computer to simulate what Sycamore does, it would take much longer, at least days, perhaps considerably longer than that. So the quantum chip nestled inside a dilution refrigerator can, at least for certain purposes, overpower a classical system that occupies 2 tennis courts and consumes megawatts of power. And furthermore, the cost of the simulation grows exponentially as we continue to add qubits, and is soon, with a few more qubits, far beyond what classical computers can foreseeably do. Now, the particular task performed by Sycamore is not of particular practical interest other than for demonstrating quantum computational supremacy, but nevertheless, this is a real milestone indicating that hardware is now working well enough to produce meaningful results in a regime where classical simulation is difficult, and that encourages us to think about more practical applications. A name that has become common for the era that we're now entering is NISQ, Noisy Intermediate Scale Quantum. Intermediate scale to remind us that we now have devices with a sufficient number of qubits that it's very difficult by brute force to simulate what the quantum device does with our most powerful classical computers. Noisy to remind us that these devices are not error corrected, and the noise is a serious limitation on their computational power. For physicists, the NISQ era is exciting. It means that we have new tools for exploring the physics of highly entangled quantum states of many qubits in a regime which has never been experimentally accessible before. And there might be practical applications of broader interests of NIST technology, but we're not sure about that yet. We should think of NISQ as a step towards the more powerful quantum technologies that we're hoping to develop in the future. I do expect that quantum computing will eventually have a transformative effect on humanity, but that might still be a ways off. Really not sure how long it's going to take to get there. Now, if we had perfect qubits, if we could execute entangling quantum gates with perfect fidelity and do deep circuits with a relatively modest number of qubits, a few hundred, we could run applications in physics and chemistry and material science, which would be of interest, which would surpass what we can do with classical computers. But the catch is that we don't have perfect qubits. We don't have perfect entangling two qubit gates. In particular, if we optimistically say that we can reach gate error rates of 0.1%, better than what we've seen so far in multi-qubit devices, then to run some of these applications would take something like 1 million or more physical qubits. And of course, that's going to be a big challenge. What makes those numbers so high is just that the overhead cost of doing quantum error correction is substantial. Our best current path to scaling up quantum computing is the surface code, as John reminded us. It has an error threshold for entangling two qubit gates of about 1%. And if we reach that physical error rate of 0.1%, about a factor of 10 below that accuracy threshold, then say if for each round of syndrome measurement in the surface code, we wanted the probability of a logical error to be 1 part in a billion, we'd need over 500 physical qubits in a code block. It's been estimated that if I wanted to run Shor's algorithm to break the RSA crypto system, I would need over 1,000 physical qubits per logical qubit, and altogether millions of physical qubits. So that's going to be a great challenge. What would be very helpful would be if we could improve gate error rates by a substantial amount. So I think it's important that people are currently exploring a variety of ways to do more hardware efficient error correction at the device level. And we heard something from Michelle about that. These ideas are still at an early stage. We don't know how well they'll pan out. There are big questions that John raised earlier about scaling them up to large systems. Nevertheless, I think these are very important corrections and directions to pursue, and we can anticipate that these combined with surface coding or other fault-tolerant methods could be a more direct path, an earlier path to scalable quantum computing. And as I already emphasized, a surprising development could change the outlook very suddenly. Okay, so that's about the first half of my talk. And in the second half, I'd like to say a little bit about something we've been working on in the last couple of years with amazing collaborators, Robert Huang and Richard Kuhn, more recently joined by Victor Albert and Giacomo Torlai, on what we call classical shadows of quantum states. So what's the idea of classical shadows? Why should you care about it? You can think about this as an efficient way, feasible in the lab today, of converting quantum data, complex many-qubit entangled state, to succinct classical data, which can then be used to recover or estimate properties of that many-qubit quantum state. Now, as you know, it's possible in principle to do complete quantum state tomography to characterize a quantum system, but the cost of that is exponential in the number of qubits, so quite infeasible for the quantum systems people are now building. What we would like is a tractable protocol for characterizing a quantum state, which is experimentally reasonable, which allows us by efficient classical processing to infer properties of the state which are of interest, and to do so with some rigorous guarantee that our estimates are accurate. And here's an example of something we can prove. Suppose we have an n-qubit quantum state, and might be quite large, but what we're interested in estimating are the reduced density operators of subsystems of R qubits, any R qubits in the device, but where R is some constant. And we'd like to do so with some bounded error for each one of those subsystems. We have access to multiple copies of the quantum state, so we can do repeated measurements. And here's what we do, something very simple. For each copy, we measure each one of the qubits uniformly at random in one of the Pauli bases, the X, Y, or Z basis, something not so hard to do in the lab. So each such measurement gives us a snapshot of the quantum state, and the collection of capital T snapshots on T copies is what we call the classical shadow. And what we can show is that given the classical shadow, we can efficiently compute all of these reduced density operators with the desired error with the high success probability. And the number of copies that we need scales very modestly with the number of qubits, like the log of the number of qubits. But the cost does rise exponentially with the size of the subsystems for which we want to estimate those reduced density operators. We can use this to estimate expectation values of operators, local operators, correlation functions, expectation values of local Hamiltonians. We can also estimate nonlinear properties like Renyi entropies that depend on those reduced density operators. So one thing we're currently interested in is combining this classical shadow formalism with classical machine learning to learn things about quantum states, to solve problems in many body quantum physics. This is a topic which has drawn a fair amount of attention in recent years, but most of what's been done has been heuristic, and we were interested in whether we can prove something about the efficiency and reliability of such a procedure. And we succeeded in doing so in two settings, which I'll briefly tell you about. So the first setting is this. Suppose we have some family of Hamiltonians smoothly parametrized by some real parameters, and we have access to ground states of these Hamiltonians for values of X that we sample. And we do whatever we like with those samples during the training phase of our machine learning algorithm. And then we use the classical information that we collect during training to predict the properties of ground states for other values of X, other Hamiltonians different from those that are encountered during the training phase. So an example of something we might want to predict is the expectation value of some sum of local operators, like the Hamiltonian itself. And the idea that we're pursuing is that when presented with a quantum state during training, we perform that randomized Pauli measurement that I described, something easy to do, and that provides us with the classical shadow, and then we train on the classical shadows. And then during the prediction phase of the algorithm, we don't use a quantum platform at all. For new values of X, we use a classical machine learning algorithm to learn a succinct classical representation of the ground states of those new Hamiltonians. And we can then predict properties of those ground states. It turns out that you can show the learning is efficient. We don't need so many copies, and the processing that we need to do is easy if the properties that we're trying to learn vary sufficiently smoothly as a function of X. And you can actually prove that's true for sums of local operators in ground states of gapped Hamiltonians. That is, if we're guaranteed that the energy gap between the ground state and the first excited state throughout the parameter regime of interest is bounded below by some non-zero constant. So the learning is classical. We convert the quantum states to classical shadows. The prediction phase is completely classical. We learn classical shadows, and from those we predict the properties. So just to illustrate this, we've done a number of numerical experiments to see how well it works. Here's one. Inspired by an actual experiment, we considered a one-dimensional array of Rydberg atoms. You can just think about this as a chain of qubits with a Hamiltonian that depends on two real parameters, whereas we increase the detuning, that favors the qubits wanting to be in the state 1 instead of 0. As we increase the interaction range, that disfavors nearby qubits wanting to both be in the state 1. And the competition between those effects produces this interesting phase structure. So what we do is we sample different values of the parameter space. And so we can do a numerical experiment. We use DMRG to find the exact answer, which we can do for this 1D chain. Then we simulate this process of generating the classical shadow. The values that we sampled are the 20 values here, indicated by gray circles. And then we use our machine learning algorithm to predict properties at these test values of the parameters indicated by the diamond, the star, and the cross. So for example, in the case of the diamond, from DMRG at that point, we can see how we could choose any local operator we want, but let's say we're interested in the expectation value of poly operator Z as a function of position along the chain. Then the pink plot here is the results from DMRG. The diamonds are the predictions of the machine learning algorithm, and they agree pretty nicely. If we did something more naive, which is to try to predict at the diamond point based on nearby sampled values of the Hamiltonian, then our predictions don't work very well at all. So the machine learning really is leveraging the results from a variety of values of X in the parameter space. The truth is that our rigorous theorem does not guarantee prediction would work in this case, because it only applies if we have training data and test data from the same phase of matter. Here we have several different phases, but the numeric shows that it still works well. And the other thing that we've studied is classifying quantum phases of matter in a supervised learning scenario. So the idea is that during training, we get access to quantum states, which are representatives of different phases of matter. During training, the phases carry a label saying it's phase A or it's phase B. And then during our prediction phase, the goal is, when we're given unlabeled states, to assign them to phase A or phase B. And again, the idea of our machine learning procedure is when we encounter a quantum state during either training or prediction, we quickly measure it to get its classical shadow. And we learn to classify the classical shadows. So when we get new classical shadows during prediction phase, we can assign them to the correct phase. The procedure that we use for learning is kind of a standard one in learning theory. We map our classical data, the classical shadow of a state, to a feature vector in a very high dimensional space. And then we try to learn a linear function in that high dimensional space that classifies, if you like, a hyperplane that separates the phase A points on one side and the phase B points on the other side. And that learning is actually efficient if we have an efficient way of characterizing the geometry, the distances between states in that high dimensional feature space. And we show that can be done, but to do so, we have to make a physically motivated assumption, which is that there is some classifying function that distinguishes the phases, which is well approximated by a polynomial in R-body marginal density operators, where R is some constant. So the idea is that we, as long as the correlation length is finite, we ought to be able to sample a volume which is comparable in size to the correlation length to tell what phase we're in. And we can prove under that assumption that the learning really is efficient, that the amount of training data and the amount of processing you need to do are both polynomial in the system size. If you get closer to a phase boundary, then what happens is you need to sample a larger volume and the learning gets more difficult. But as long as the correlation length is finite, the cost still scales polynomially in the total size of the system, the number of qubits. And here too, we've done some numerical experiments, of which here I'm showing one. Here the goal is to distinguish between a topological phase and a trivial phase. By definition, topologically ordered phase has the property that we can't, with a finite depth circuit, prepare a state in that phase starting from a product state. So what we do here is we take a representative of a topologically ordered phase, namely Kitaev's toric code, and a representative of a trivial phase, namely a product state. And then we apply low depth circuits to the two states, and we ask our machine learning algorithm to try to distinguish them. when those circuits are not too high in depth. In this case, we used a toric code, which has distance 10, a total of 200 qubits, and applied random local quantum circuits to the trivial state and the toric code state. And then we can take this feature space and just for purposes of illustration, project it down to 2 dimensions so that you can see that the result of applying a low depth circuit to the topological state and to the trivial state can be easily distinguished. In fact, we don't even need the labels. We can do unsupervised learning in this case. This was for the case where we applied a depth 3 circuit to the 2 states. As you increase the depth of the circuit that you apply, it becomes harder to distinguish the phases. And once you get up to depth 5, in the case where the toric code distance is 10, then we can't nearly as successfully distinguish the trivial phase from the toric code phase. Okay, so that's what I wanted to tell you about classical shadows. Classical shadows provide us with a tractable procedure for converting a many-body quantum state to succinct classical data. And we can use that classical data to efficiently compute with a classical computer many properties of the state. With just log m copies of the state, we can compute m properties that can be characterized by local observables. And I didn't explain this, but we can show the number of copies used in our protocol really is asymptotically optimal if we're restricted to measurements on a single copy at a time, if we're not allowed to do entangled measurements across copies, which would be much harder to do experimentally. We show in in numerical experiments that our methods have an advantage in both sample complexity and classical processing time over other methods that have been used to predict properties of many body states, and that by combining classical shadows with classical machine learning algorithms, we can efficiently solve interesting problems in quantum many body physics. And the important thing to emphasize is that with the classical shadow together with the classical processing and the classical machine learning algorithm, we can solve quantum problems that might be very hard to solve using classical processing alone. The data that we get from a quantum platform is empowering us through these machine learning tools to learn things about many body quantum physics that would be hard to learn otherwise. So I think we can anticipate that in the years to come, including in the near term, these methods of leveraging classical computing with data from quantum experiments will lead us to new discoveries in quantum science and technology. So thanks for listening.
Thank you very much. That was really a great overview. Can I see if there are any questions in the Q&A or hands? Hands are difficult to see. Q&A? Okay, so I missed the hand before, which I'll come back to shortly, but there is a question which is related to the general area, which John Preskill opened up at the beginning of his talk. So let me bring up that question. What conversations does the community need to have around the ethical use of future quantum computers, just as we are conversing about ethical AI? Are these conversations taking place in the companies driving quantum computer innovation?
I think to some degree those conversations are taking place. I mean, I can't speak for all the quantum companies, but I think a lot of the ethical issues pertaining to quantum computing are similar to those confronted by AI researchers and classical computing practitioners in general. I don't think they're that fundamentally different with quantum computing. What may eventually be different is that if quantum computers are available to some entities, countries or businesses, and not more widely available, there could be a big disparity in computational power and the tasks that one could perform. The obvious implication of that being to cryptology. And, you know, some people have quantum computers and they can break widely used public key crypto systems, and others do not. This creates a kind of a differential in power and influence. Of course, the world is trying to do something about that to protect against quantum computers breaking crypto systems by developing quantum resistant computing protocols. I think that's really important to do, even if quantum computers that can break RSA and other crypto systems won't be available for a while. We should be preparing for that moment, and people are working on that, trying to settle on standards for protecting our privacy in the post-quantum world.
Thank you. There is a question: why should training from a shadow in one phase be able to protect expectation values in a different phase?
I can't really explain that. Our theory does not guarantee that would work. The numerics seem to indicate that it works better than you would expect. So it's a good question.
Ephraim Steinberg asks, does this suggest that there could be regimes where an apparent quantum advantage can be defeated by machine learning predicting the classical shadows of the quantum computer?
So if I understand the question, Ephraim, you're saying, can we use these methods even if we don't have access to a quantum platform at all, but we use classical shadows and machine learning in a purely classical approach? I guess in principle, one could do that by using classical numerical methods to find descriptions of the quantum states. And then, like I described, of course, this is what we did in our numerical experiments, simulate the measurements that produce the classical shadows and use them to predict. That might be an effective use of classical resources for solving quantum problems. I think we can say that if we have access to data which is prepared in quantum platforms, that gives us greater power. In fact, we did the following thing just to illustrate that point. One can devise local Hamiltonians which have the property that if we can predict few body observables, we can solve a factoring problem. And the quantum states, which are ground states to these Hamiltonians, can be prepared on a quantum computer, essentially by running Shor's algorithm. And so if we had access to those ground states and we just did these simple randomized Pauli measurements on them, we could solve a factoring problem, which we think is hard classically. So I emphasize that example because the quantum state is one that feasibly we could prepare on a real quantum platform, though probably not until we have fault-tolerant quantum computers. More generally, I mean, you can just, of course, we already know this classically, ground states of Hamiltonians can be hard to prepare. And that's, even true for classical spin glasses. So if we could measure ground states of classical spin glasses, we could solve NP-hard problems. And the lesson from that is that we don't expect those to be prepared in nature. Nature can't prepare those ground states. So I think it's encouraging that at least we know that states that can be prepared efficiently on quantum computers can, combined with classical machine learning, allow us to solve problems that are hard classically, but are solvable by quantum computers.
Thank you. Arthur Ismailov asks, could you comment on prospects of classical shadows with entangled measurements?
I think the question is, what if we go beyond just doing these single qubit randomized measurements? Does that give us extra power? Yes, it does. Another thing that we analyzed in our earlier paper actually is measuring stabilizers, essentially measuring commuting Pauli operators, which are not necessarily low weight ones. And that enables us to do things which go beyond what we can do with these randomized single qubit measurements. For example, we can estimate fidelities of quantum states with target states very efficiently with just a constant cost. we emphasize the single qubit measurements because they're something we can really do now in experiments. To measure randomized stabilizers, to do a random Clifford operator for a many qubit state, and then measure all the qubits, that would be more costly. It requires a depth which is almost linear in the total number of qubits, and we won't be able to do that for a while until we either have much better entangling 2 qubit gates or fault tolerance.
So I find myself in the middle of this Q&A list, and in case people didn't notice, Ephraim Steinberg has managed to clone himself. There are now 2 of them on the screen. An amazing feat. Ephraim's had a question: could this simulation of Lucan's simulator be more efficient than the simulator itself? Which of course is linked to his earlier question.
Well, I think that was intended to be a clarification of the original.
Yes, it was. So I'm not sure whether we have already done that. Okay, so let me go on. There is one last question regarding one of your first slides. Is there a clear example of a problem that we believe to be hard even for quantum computers?
Yeah, there are lots of them, including all the hard instances of NP-hard problems. We don't think that quantum computers can efficiently find exact solutions to NP-hard optimization problems. What they can do is they can speed up exhaustive search for a solution to an optimization problem running Grover's algorithm. But that's just a so-called quadratic speed up, meaning that the time on a quantum computer goes like the square root of the classical time asymptotically. And chances are that's not going to be a practical thing to do for quite a while. And that speed up may become significant in the long run. But because there's still an exponential cost, even with a quantum computer, we'll need probably fault-tolerant quantum computers of a considerable scale before we'll be able to see that advantage kick in.
Thank you. Time is running out, so I want to congratulate Professor Martinez once again for receiving the John Stuart Bell Prize, and to note that we will hopefully be having a live conference, Center for Quantum Information, Quantum Control, a live conference next year, hopefully around August. So I would suggest everybody look out for it, and please plan to attend. So thank you very much, everyone. And here we go again, have a good afternoon, a good morning, a good evening, wherever you are. Thank you.
Thank you again. Bye-bye.
Bye-bye.
Thank you, everyone.